Okay, so the next problem in section 3.1 is number 29, and that states the directions say locate the absolute extremum of the function on the closed interval. The function that they give us is y equals 3 minus the absolute value of t minus 3 on the interval from -1 to 5. So we're trying to find the value that this function attains at a maximum and the value that this function attains at a minimum. So one way that we want to make sure, first let's make sure that this function is indeed continuous on this interval. We'll take we have this absolute value. One way to define the absolute value is with a piecewise function where we say we split our function into two cases. It'll be 3 minus, and we're going to multiply this t minus 3 by a negative, right? So I'm going to multiply it by a negative, so let's just make that positive right there, t minus 3. In the case, or where, t minus 3 is less than 0. So if I have t minus 3, and that's some number which is less than 0, then I am going to get a problem, or excuse me, I'm going to multiply that by a -1 in order to make it positive again. In the other case, where t minus 3 is greater than or equal to 0, then I'm just going to leave it alone, because I'm going to get a number which is positive, so I'm just going to leave that alone to be just t minus 3. Okay? So this simplifies out to be 3. I can drop this grouping symbol here, so I get 3 plus t minus 3 in the first case, and we can simplify this inequality to be by adding 3 on both sides. Those are in cases wherever t is less than 3. I also note that I get some additive cancellation here. Whoop, whoop. And over here I have this negative sign that I need to distribute to both terms that are here. So that'll be 3 minus t minus 3. Oh, I'm sorry, plus 3. Say what I do what I say. So this is going to give me, in my first case, a value of t, in my second case, a value of 6 minus t. So, is this function continuous? Well, t is continuous on an entire interval, and 6 minus t is continuous on an entire interval. So the question becomes this transition point, where I go from, and this guy right here is t greater than or equal to 3. So, two cases again, t less than 3, t greater than or equal to 3. So what happens at t equal to 3? Is my function going to be glued together at that point? So as I approach the limit as t goes to 3 on the left of this function y is going to be the same as the limit as t goes to 3 on the left of just t, which is equal to 3. The limit as t goes to 3 on the right, so as I approach it on the positive side of my function, will be the same as the limit as t goes to 3 on the right of 6 minus t, which is equal to, I can just use direct substitution on this, and then it would be t minus 3, which equals 3. So my function's glued together. As I approach on the one side, I get the same value as I approach on the other side. So my function's continuous. That's good. What about the derivative at that location? So let's just boil it down to, here is my function definition. A shortcut method for finding the derivative of a piecewise function is to take the piecewise derivative of all the functions that compose it. right? That make up this definition of this piecewise function. So y prime is going to be equal to, in the first case, the derivative of t is 1 for all values which are t less than 3, and the derivative in our second function here is 6 minus t, and that will be the derivative of 6 is 0. The derivative of negative t is negative 1, right? And that's for t, well, maybe greater than, but what about equal to 3? This transition point right here at 3. Remember that the derivative is defined as a limiting process. So the value of the derivative as you approach on the right should be the same value as you approach on the left. It should be glued together and continuous, right? Just like our function, right? So the derivative at t equal to 3, since the left and right values don't approach the same value, ends up being at t equal to 3, our derivative, y prime, does not exist. Okay? So, and you can see that because if I look at my function, my original function, which is y equal to t for t less than 3, so if I just kind of quick and dirty plot this. So here is my graph here. I have t all the way up until this point right here at 3. And then all of a sudden, I change over to 6 minus t. It shares a value of 3 right here, but minus t looks like this. So this is what my function looks like. So on this side as I'm going along, right, my derivative looks like it's 1. The slope of this line is 1. So slope of this line is 1, so its rate of change is constant, is equal to 1 as you approach here. So it looks like the derivative is 1 as you approach it on the left. As you approach it on the right, this value of 3, the rate of change looks like it's negative 1. The slope of this line right here is negative 1. So my derivative approaches two different values at this point, so which one's better? Well, neither are better than one or the other, so we would say that the derivative does not exist at that point. So that makes it a critical number. Critical number at t equal to 3. So, is there any other critical numbers? Well, critical numbers are defined either where the derivative does not exist or the derivative is equal to 0. And clearly this derivative can never equal 0 because it's either 1 or it's negative 1. Or it doesn't exist at t equal to 3. But it's never 0, so this would be the only critical number that occurs. So this problem asks us to find the absolute extrema of the function. The absolute extrema of the function can either occur at, when you describe it on an interval, it can either occur at the endpoints. Our endpoints are negative 1 and 5, or at the critical numbers that occur between the endpoints, or maybe at the endpoints themselves. And 3. So this is an endpoint. This is a critical number, and this is an endpoint. All we have to do is evaluate what the function is at each one of these. So we get 3 minus the absolute value of negative 1 minus 3. So negative 1 minus 3 is negative 4. The absolute value of negative 4 is 4. So 3 minus 4, that is negative 1. At 3, it is 0, right? So, t minus 3 becomes 0. So 3 minus the absolute value of 0, which is 0. So that is just 3. And then at 5, we have 3 minus 5 minus 3 is 2. Absolute value of 2 is 2, so 3 minus 2 is 1. So we can look at this and we can say, hey, this guy right here, where these are my x values and these are my y values. This guy right here is going to be my absolute min. And this guy right here is going to be my absolute max. Okay? So we have an absolute min value and an absolute max value. And if we confirm that with a graphing calculator, where I put in 3 minus x minus 3. Oh, and I need to throw in that is the absolute value function. We have to put x because it doesn't recognize what t is. So for example, if I put t in here, hey, I don't understand 3 minus the absolute value of t minus 3. The reason for that is because it's looking for an expression in terms of x. Oh, and I didn't correct that. That goes from, let's see, what was our interval? From -1 to 5. -1 to a positive 5. And I hit enter. So right at x equal to 3, I have a value of 3. At -1, I see that it's lower than over here at this endpoint. So our max is here and our min is here, just like was predicted by what we did and our work. So that is number 29.